This presentation is a design review of an offline boost regulator utilizing a new way of eliminating the difficult to deal with non-sinusoidal harmonics generated by switch mode regulators. I have patented the technique titled Electrical Circuits for Power Factor Correction by Measurement and Removal of Overtones. The first part of the presentation is a review of what power factor is. The second part is a discussion of the circuits described by the patent. The third part is the design review of an offline boost converter designed with the technology of the patent. And the fourth part is a brief discussion of the extension of the new method to other circuits, including three-phase PFC. As a review of power factor correction, an electrical generator makes electricity for the power grid, of course. The general shape of the voltage of the generator puts out is sinusoidal. The load current should be sinusoidal and in phase, but may not be. This causes power loss and other serious problems in the generator and the distribution system. Non-sinusoidal loads cause a multitude of problems in the generator and the distribution system. If a current wave is non-sinusoidal, the higher harmonics cause power loss in the system and inefficiency because the system is designed for 60 hertz operation. In addition, the generator may find itself alternately slowing and accelerating in strange ways over a cycle. Either condition is acceptable. Power factor correction is the process of changing poorly conditioned loads into loads that look resistive, where the current follows the voltage in a sinusoidal waveform. This slide shows graphically the two general kinds of current distortions which need correction. You want to change the bad waveforms into good ones by dynamically changing the current into the load, i.e., correcting the load current. The blue line is the sinusoidal voltage. The black line is the ideal sinusoidal current wave. The purple line is a phase-shifted load current, here into a somewhat capacitive load. This problem is usually caused by motors, but with the opposite phase shift. This is not our problem. The red line is a distorted load current form, which is usually the problem with switch mode regulators. This is the subject of the present discussion. It is the job of power factor correction to modify the current draw of the load circuit such that the distortions from the ideal are eliminated. This invention is a new way to do that correction for switch mode power supplies utilizing negative feedback in a closed loop system. This method will be fully explained. Every electronic device, TVs, computers, battery chargers, etc., that plug into the power grid can cause problems. Problems are caused by the power supplies which convert AC mains power to DC power for the device to use. Every AC to DC converter should have a power factor correction, even if only for power loss. The biggest power factor losses and problems occur in the power grid and the generator, not in the load. Ideally, every AC to DC converter should have power factor correction over the widest possible range, from light load to heavy load and over all voltage inputs. The new technology makes this possible. Power factor correction for switch mode power supplies has been available for many years. The circuits are generally complicated and can be difficult to implement because of the requirements for high-speed current sensing loops, high current precision resistors, poor light load capacity, etc. This new approach does away with this by removing the phase shifts and non-sinusoidal deviations easily and over a wide range of currents and voltages. This is accomplished with precision negative feedback. No high precision resistors, no high-speed current sensing, constant frequency operation. It's simple circuit for easy customer use. At least 100x current dynamic range, at least 2x voltage input range, can be used with virtually any switch mode topology. It doesn't have to be used with a boost or a buck or a boost buck. It can be used with any. Over most of the range, perfect power factor correction for mains efficiency is possible. It has the lowest circuit power dissipation. It has less expensive external components. It has more noise immunity because it can be used at constant frequency. Most of the current power factor correction circuits have variable frequencies. My approach to the power factor correction is new and I believe substantially superior to the present technology. I have been granted a patent on this topic. In this presentation, I explain the basic circuit technology underlying the patent and show some simulation results that validate the claims of the patent. Of course, I would love to sell or license this patent to you. Here is my brand new patent front page, electrical circuits for power factor correction by measurement and removal of overtones. It is an analog version of my previous digital patents. This invention may be worth hundreds of millions to some company able to capitalize on it. It broadens the PFC market. It is easy for the product designer to use. It is accurate over a wide dynamic range. It saves power both on chip and in the AC network, and it will work with any switch mode topology. I am Bob Rethel. You may not know me, but you certainly know my most famous patent, the SenseFET, here graciously named current sensing circuit. It was awarded in 1984 while I was working at Motorola in the Semiconductor Research and Development Labs. I developed this sensing technique during 1982 and 83 as I was designing a semiconductor headlight switch for Delco in Kokomo and needed a lossless way of limiting inrush current. I developed this patent as we were working on the Motorola version of Power BCD-MOS. I thought we were one of the first to develop it, but Motorola chose not to pursue the development, but Delco did with the European supplier. It was also in SRDL that our little group worked on the Motorola version of Power DMOS. Our group did all of the process development and device design for the Motorola products. After Motorola, I went to GE to help them develop a Power BCD-MOS technology, which we used for a huge IBM contract. Then I came to National to help develop their version of Power BCD-MOS. Here is a list of my patents. It is a fairly wide-ranging list of device, process, and circuit inventions from a substantial career in power management. There are 41 on the list, with this one more to add. The following block diagram is a very simplified view of the technology. It shows how the closed loop works, and details will follow. We start at the upper left with the AC power, the rectifiers and input filters. Then there is a voltage controlled resistor with the control voltage V control. The operation of xamp1 is to minimize the difference signified by VDIF. One input to xamp1 is a rectified sine wave reference divided down from the input supply. The second input is the value of the sensed current through the voltage controlled resistor. This voltage, VDIF, will contain all of the harmonic content of the measured current, as will be explained. The amplifier diffamp amplifies the VDIF difference and subtracts the power factor voltage from the feedback voltage, VER, to produce the sum voltage. The sum voltage contains information both to regulate the output voltage of the regulator and to remove the non-sinusoidal harmonics from the input current. It is used by the switch mode regulator with its normal feedback loop to regulate the output and to control the power factor. As the vastly simplified block diagram shows, the power factor is corrected by closed loop error correction. To understand how this happens, we need to show how the voltage VDIF contains the overtones to be removed. We will develop the full circuit step by step, so bear with me. This is the simplest form. If you put a current I load through the voltage controlled sense resistor, which could be a low voltage NMOS device, the operation of xamp1 is to make VDIF as close to zero as the gain of the amplifier will allow. VDIV equals Vsense. If you make Vref a voltage divided down from a rectified AC voltage, then because Fsense is forced equal to Vref, the Fsense voltage will be in the form of a rectified AC wave, regardless of the input current, here shown as a very distorted sine wave in the upper right hand of the slide. This circuit is modified. Xamp1 becomes 2 amplifiers, but that changes nothing from the previous slide. What changes everything is the inclusion of a low-pass filter between xamp1 and xamp2. V control is now a very slowly changing voltage, much slower than the AC waveform. The action of xamp1 and xamp2 is to make the signal VDIF, shown on the lower right. The average of VDIF is 0, so it contains all of the non-sinusoidal deviations of the input current. When the low-pass filter is added, then the error signal VDIF is still forced to be small, at least on the average. This minimum is just the average over a cycle being made 0. Of course, the current sense of a switching regulator contains a large amount of switching signal. This interference must be removed for an accurate offline current measurement. This is done by introducing a second low-pass filter. This filter admits some 20 or so harmonics of the fundamental 120 Hertz rectified sine wave. We add the bandpass filter around the loop of xamp1. The output of xamp1 is a low impedance output, so by adding C43 and R94, we can band limit the content of the VDIF signal. Here we have chosen 2 kilohertz. It is not critical. The switched current is indicated by the input current on the left. With the 2 kilohertz low-pass filter, we can recover a very good representation of the low frequency distortions of the ground current from the ideal. The departure is shown in the plot at the bottom center. The capacitor and resistor form the pole of a first-order low-pass filter. Any output resistance of xamp1 will put a 0 in the frequency response. Typically, the output impedance of xamp1 should be probably 10 to the 4th times less than the resistor value. Alternatively, a passive second pole could be introduced into the feedback network to cancel an inadvertent 0 due to the amplifier output impedance. So now we have a signal which can be used to remove spurious harmonics and phase shifts from the switch mode regulator input current. This is the VDIF difference signal to xamp1. It is the voltage difference between Vref and Fsense nodes. The signal is forced to be small by negative feedback. This is the basic schematic of what we just described. The amplifier div amp will force the signal VDIF to be small by negative feedback and by the gain of the amplifier. Power factor correction signal is subtracted from the normal feedback signal The sum signal is used to control the regulator. In terms of stability, the current loop generally has little problem because of the low poles in the loop. It must be emphasized that the power factor correction signal from diff amp must be a first order correction to the normal loop. The amp must always be able to override the PFC circuit diff amp. The PFC circuit is simply a first order correction to the 0th order signal. The gain of diff amp is not an issue. What is an issue is the magnitude of the relative signals. The amp signal magnitude must always be able to override the magnitude of the signal from the PFC amp, diff amp. The amplifier diff amp provides a first order correction to the main loop of the switch mode regulator. The amplitude of diff amp must be adjusted vis-a-vis the main amp. The amplitude of the output of diff amp cannot exceed that of amp, or regulator may not regulate the output voltage. The gain of diff amp can easily be set for stability because the loop frequency is low. The higher the better. To prove the concept, I did simulations of an offline boost regulator with inputs of 120 and 240 volts RMS and a 400 volt output voltage with various resistive loads. The simulations covered a range of about 100x in current from 30 milliamps to 3 amperes. Most of the devices, amplifiers, etc., were behavioral models to improve speed and aid in spice convergence. The waveforms are shown from this simulation. This is a cleaned up schematic for simulation. I represent here the gate drive circuit by a small block. This is a constant frequency pulse width modulated regulator. There is an input filter, the voltage controlled resistor, the switch mode switch, the switch mode inductor, the power diode, the output capacitor, the output load, the normal error amplifier, X-amp1 and X-amp2, low pass filter, band pass filter, the diff amp, summing resistor, and the error signal. On the bottom set of traces, where the half cycle is 8.33 milliseconds, the top plot is the overlay of Vref and Fsense. You can see that the circuit has worked well. The second plot is the value of Vdiff, which has been forced by the system into the millivolt range. The third plot is the trace of the summed error signal near 5 volts. You can see where the Vdiff rises, the Vref signal falls as it should. The last trace on the bottom plot are the input and output of the low pass filter following X-amp1. You can see that the output should be the average of the input. This is clearly not the case, but probably reflects the fact that the total simulation time is a half second, while the low pass filter time constant is a half second. It probably reflects a small lag in the filter response. The plots in the upper right-hand corner are the large signal response of the switching regulator circuit. In the top set of traces, the red line is the ramp voltage for the PWM circuit. The blue trace is the error signal, and the green line is the gate drive signal. The bottom trace is the current in the inductor. The max current of the Vdiff amp is 70 microamps, while the max current in the amp is 170 microamps. This reflects the requirement of the PFC correction being a first order correction. The gain of the diff amp is not particularly important as long as it is high enough. These plots are detailed of the plots shown on the previous slide. On the upper set of plots, the time frame is the 10 microseconds. It's the PWM signal of 100 kilohertz. In the upper plot, the red trace is the ramp for the PWM signal, and the blue line is the error feedback signal, and the green line is the gate drive for the PWM switch. The bottom trace is the current in the inductor. You can see as the power divide, as the switch turns on, the inductor charges, and as the gate turns off, the inductor discharges into the load. The second set of traces are at the line frequency. Note a half cycle is 8.33 milliseconds. The top trace is VREF overlaid by fsense, and you can see they overlay very well. The second trace is VDIF, just the difference between those two signals, and it's in the millivolt range. The third trace is the error signal, the sum of PFC and the regular error, VER. The fourth set of traces is the input and output of the low-pass filter. You can see the low-pass filter input is irregular and the output is very smooth. I did 4 simulation sets to 120 volts, swept from 300 milliamps to 30 milliamps, swept from 300 milliamps to 3 amperes, and then 240 volts, swept from 300 milliamps to 30 milliamps, and then swept from 300 milliamps to 3 amperes. And this simulation is more difficult for PFC, and the circuit is the same for each run. First set of simulations, 120 volts in, is an easier simulation because the difference between V in and V out is greater. This is a naturally better condition for PFC. I did the 2 slides from 300 milliamps to 30 milliamps and 2 slides from 300 milliamps to 3 amperes. The total is 100x in current. It's got a very large dynamic range. In this plot, the input was 120 volts RMS, and the output was swept down from 300 milliamps to 30 milliamps. The first plot shows input and output. The second plot shows input current in red and a sign reference signal in green, and output current in blue. The third plot is the differential signal VDIF, the source of the power factor correction. The fourth plot is the main error voltage, also called sum, which is the combination of PFC and output feedback signals. The fourth plot shows the summation process of the PFC signal in the output error loop. Red is the current output of the error amp, blue is the current output of the diff amp, and green is the combined sum of the two. The input current remains sinusoidal and in phase over the full range. In this plot, the lower plot in this slide shows the 100 kilohertz switched inductor current envelope in blue. The power factor correction is in the details of this current, both magnitude and duty factor. In other words, how the power factor correction works is in the details of this blue signal. In addition, there is the average inductor current shown in red. Here the current is ramped upward from 300 milliamps to 3 amperes. The first plot is input and output voltage. The second plot is input current in red, sign reference in light blue, and output current in dark blue. The next plot is the VDIF power factor correction signal. The next plot is the summed error signal, VER. On the fifth plot, the summing currents are shown. Red is the output feedback. Dark blue, the signal for PFC, and green is the sum signal. Again, output current remains sinusoidal and in phase over the full range. This shows that PFC method has a substantial dynamic range between these two sets of current. The current is varied over 100x from 30 milliamps to 3 amperes. Same conditions as the last plot. The bottom trace in the blue is the envelope of the inductor current. The green is the average inductor current, which should be sinusoidal. What must be mentioned is the importance of a proper input filter arrangement such that the high peak currents are sustained by the low pass filtering on the input. These filters also store energy for the times in the rectified AC where the voltage goes to zero. I did a second set of simulations with V in 240 volts. This is a harder PFC condition because of the difference between peak V in and V out is smaller. Again, these plots demonstrate a power factor correction over 100x in current range. These plots are high input voltage in and ramping the output current from 300 milliamps to 30 milliamps. The top plot shows input and output voltage. The second plot shows input current in red and sine wave in light blue as a reference, and output current in dark blue. The third plot shows the harmonic content signal V diff, and the fourth plot shows the composite V error signal. The fifth plot shows the three currents summed to make the V error signal for the regulator as the green line. The red line is from the feedback amp, and the blue line is from the power factor correction diff amp. Like the previous plot, this is with high input voltage sweeping from 300 milliamps to 30 milliamps output current. The interesting thing in this plot is the reaction of the circuit to high voltage. The top plot shows input voltage and output voltage. The second plot shows input current red and a sine wave in light blue as a reference. Output current is in dark blue. The third plot shows the harmonic content V diff. The fourth plot shows the composite error signal. The fifth plot shows the envelope of the inductor current. The effect of the high input voltage can be seen as the power factor correction reduces the current at the centers of the cycle to make the ground current sinusoidal. The green line is the average inductor current, which should be sinusoidal. This plot shows an anomalous behavior with a high voltage in and low current out. A phase shift develops. In the second plot, the dark blue line is the input current and the light blue line is a reference sine wave. The red line is the output current. The phase shift is noticeable and corresponds to a power factor of about 0.9. I was unable to account for this phase shift, but presumably it comes from the input filter capacitor. This slide shows the response with high voltage in. Upper plot is input and output voltage. The second plot, blue, is output current from 300 milliamps to 3 amps. Red is the input current. Light blue is a sine wave reference. The third plot is V diff, the power factor difference signal. The fourth plot is the composite error signal with the power factor correction and main loop error signals. The last plot are the currents which make up the composite error signal. Red is the current from the output error loop. Blue is the power factor correction signal, and green is the composite error signal, the sum of the other two. This is like the previous slide, but with the addition of the switched inductor current envelope in the fifth plot. The dark blue is the inductor current envelope. The green trace is the sinusoidal average current, and the red trace is the output current. This is a detailed view of the high current end of the previous plot, showing a finer detail of the inductor current control and the sinusoidal character of the input current in the second plot. The third plot is the envelope of the inductor current in blue. In the fourth plot, the composite error voltage is shown in the red-green line. In the fifth plot, the power factor correction signal VDIF is shown. This slide shows how the power factor correction corrects the main error signal to make the composite error, shown as V error in the third plot. The VDIF signal in the fourth plot mirrors the current correction in green from the PFC circuit. The red line is from the feedback error amplifier and the blue line is the composite signal. I adapted this to a current sense transformer. This technology can be adapted to virtually any switch mode engine as long as it has an error signal which can be corrected by the current correction circuit. In this case, a current transformer has been adapted to be used with this technology. It allows for high-side current sense, which might be adapted to multi-phase systems and phase balancing. In this circuit, the current is sensed by the current transformer. This gives the circuit quite a bit of flexibility in how to sense the input current. This method can be used with very high-power circuits with high current. A current transformer allows the sensed secondary current to be orders of magnitude less than the primary current, where it can be integrated into an output transformer for a transformer flyback circuit. It also allows the application of easy PFC in multi-phase converters with a current transformer in each phase. The magnitudes of each phase can then be balanced for a multi-phase power factor correction, where each phase is corrected separately, but each phase is subsequently balanced against the others. The device, M1, connects the transformer to the current sense resistor as a switch. When the main inductor is discharged, the switch M1 opens and forces the residual energy in the current transformer to be discharged in the more resistive elements of the sense circuit. In conclusion, I want to thank you for watching this presentation. I hope you found it interesting. I do want to leave you with these advantages. This is a technology that broadens the application of power factor correction. It is a simple circuit. It has excellent performance. It's very easy to apply. It's very good efficiency. It has great switching noise control at constant frequency. It is simple enough for any offline application of any kind of switching regulator. Thank you very much.